Welcome to this lecture on electromagnetic interference, or EMI as it is generally referred to. My name is Jim Moreland and I'm the Head of Rail Systems at ENOTRAC UK Limited, a role that includes responsibility for electromagnetic compatibility issues. The lecture covers the basic principles of EMI with an emphasis on railway systems. You'll find out about sources and victims and how the former cause problems with the latter. And to finish off, there are a couple of real-life case studies. In this lecture, I will introduce the basics of EMI, starting with its definition. I introduce the concept of sources of EMI and their victims, and describe the four mechanisms that can couple them together. There are some examples of common sources of interference, both in general and in the railway domain, and of course examples of victims. I also touch on some related topics that may or may not be EMI. And finally, there are two real-life case studies. By the end of this lecture, students should appreciate the problems that may be caused by EMI. They will understand the four basic coupling mechanisms and be able to identify where each one is likely to be applicable.
Is there a legal definition of EMI? Well, the ruling legislation up to the end of 2020 was the EU EMC directive. However, post-Brexit, this is no longer in force. However, the UK EMC regulations, which transpose the directive into UK law, are still in force, as are being updated to exclude all reference to the EU. The text is more or less the same as what was in the directive. So what does it have to say? Defines EMI by saying what it is not. The electromagnetic disturbance generated does not exceed the level above which radio and telecommunications equipment or other equipment cannot operate as intended. Note the emphasis on interference with communications. The purpose of the directive is to protect the broadcast spectrum. Electromagnetic disturbance means any electromagnetic phenomenon which may degrade the performance of equipment. A disturbance may be noise, an unwanted signal, or a change in the medium itself. However, electromagnetic phenomenon is not defined. Most people think of EMI in terms of radiated emissions, broadcast radio and TV, mobile phones, Wi-Fi, etc. But it includes the whole frequency spectrum from DC to gamma rays.
So, sources and victims. The compatibility definition implies that there are two parties involved in EMI. There's a source that generates the interference and a victim whose operation is degraded or even perhaps prevented by the interference. It is generally assumed that the source is not affected by its own interference, although this is not always the case in terms of cases of badly designed equipment. Note that any equipment can act as both source or victim under different circumstances. For example, a mobile phone reception can be adversely affected by the electromagnetic fields generated by nearby high voltage power lines. On the other hand, a mobile phone is itself a powerful generator of electromagnetic fields and can cause problems if used too close to electronic equipment.
So what are the four interference coupling mechanisms? They're presented briefly here and will be elaborated on the following slides. Capacitive coupling is through stray capacitance, also known as parasitic capacitance. Actual capacitors count as conductive coupling. Conductive coupling is through an intentional or unintentional galvanic connection. This definition includes stray resistance, which can be important on railways, where there can be a low resistance between rails and earth. Induced coupling is standard near-field magnetic induction, and radiated coupling is far-field electromagnetic radiation. The terms near and far field will be explained later. Capacitive coupling. Capacitance exists between any two conductive surfaces separated by an insulator, also known as a dielectric. And remember that air is a good insulator, very good insulator. If you combine the equations for capacitance C and capacitive reactance XC, you can see that the impedance of a capacitor is proportional to the distance between the conductors and inversely proportional to their area, and also inversely proportional to the frequency of the current. To get significant levels of interference current, XC must be small in relation to other paths in the circuit. And this implies that either D is small, A is large, or the frequency is high, or a combination of those three factors. Some examples. For a computer printed circuit board, D can be very small, less than 1 millimeter, and the frequency can be in hundreds of megahertz or even gigahertz. So a piece printed circuit board layout can be critical. Another example is wound components, motors, transformers, etc. The frequency is generally low, but D can be small, thickness of the insulation less than 1 millimeter, and A can be quite large. For example, a metro-sized three-phase traction motor has about 25 nanofarads capacitance between the windings and the motor carcass. But what does that mean for EMI? Let's do a quick calculation to see what the significance of this is in terms of electromagnetic interference. If we have 25 nanofarads of stray capacitance per motor and 4 motors per converter, that gives us 100 nanofarads of stray capacitance per converter. Now, if you have a metro with audio frequency track circuits, for example, operating around 5 kilohertz band, then the reactance of the capacitor at that frequency is approximately 300 ohms. The converter is switching and applying pulses of 750 volt DC peak to peak to the motors, and this is applied to the stray capacitance to earth. And that gives approximately 1 amp RMS of current into the earth, and that is quite a significant amount of interference current for these audio frequency track circuits. One point to consider, why is this form of coupling not an issue for network rail DC third rail systems?
Conductive coupling. There's always a finite resistance between any pair of conductors. This is generally too high to be a serious source of interference, notable exception being stray current from the rails of an electrified railway. The interference path is generally via galvanic connection, i.e. solid metal to metal. Often it's a shared return circuit. Conductive coupling is generally in the power to audio frequency range. At higher frequencies, the circuit stray inductance tends to block the current.
A common example of conductive interference is harmonic content on the mains 50 Hz supply caused by other loads that share part of the distribution circuit. It could be in your own house or from a neighbour fed from the same 400 volt transformer, or even further up the distribution chain. The lowest level of shared circuit is called the point of common coupling. This real example is of a keen musician with a home recording studio who had the misfortune to share his 400 volt main supply with a large controlled rectifier operating an elevator. Recordings were made of the 240 volt waveform in the studio. The first plot shows the mains voltage with the lift off. The waveform is a smooth 50 Hz sine wave, as you might expect. The second one shows the effect of the lift operating. The notches in the voltage here are typical of rectifiers. UK limits for power quality are set in Engineering Recommendation G55. In this case, the harmonic content of the rectifier current exceeded the limits and the operator had to add filters.
A second example of conductive interference is in railway track circuits. The track circuit current is shown in green here that circulates between the transmitter and the receiver via the rails. The train draws its current from the substation along the overhead line or third rail, back into the rails and back through the track circuit. As you can see from the orange dashed line, some of the train return current actually flows through the receiver. Now, if the train current contains components at the track circuit frequency of operation, then there can be problems. One example I came across was a receiver tuned to 9.6 kHz on a DC railway, where the main harmonic currents are typicals of 600 Hz, multiples of 600 Hz from the rectifier.
In inductive coupling, there is no galvanic connection. Current in one conductor loop can induce voltage in an adjacent conductor loop. Imagine it as like a poorly coupled transformer with just a single turn on each side. Although the transformer ratio is low, the loops can run in parallel over long distances, especially on a railway, where you have line-side cables running for many kilometres. The equation shows the voltage induced per unit of length in the victim loop by one of the source conductors. It's derived from the Biot-Savart law applied to parallel conductors. The example shows the contact wire as the source with the conductors in the line side cable as the victim. Repeat the calculation for all the source conductors and then sum the contributions, making sure you sum them vectorially. And finally multiply by the length of track where the two loops are in parallel. The critical quantity for interference in line-side cables is not the induced voltage along the cable, known as the longitudinal voltage, VL, but the voltage across the load terminals, known as the transverse voltage, VT. In a two-core cable, the distance from the source conductor to each of the two victim conductors is more or less the same, so the voltage induced along each core is also more or less the same, and the transverse voltage, being the difference between the two longitudinal voltages, can be very small, even over several kilometers. Note that the longitudinal voltage is important for human safety, electrical shock hazard, and it limits the maximum length of continuous line-side cable.
Radiated coupling is generally taken as electromagnetic emissions in the far field, where the electric field dominates. Generally, this is taken when the distance from source to the victim is greater than 3 wavelengths. For example, FM radio of the far field starts about 10 meters, while for Wi-Fi the far field starts about 400 millimeters. Any conductor in the victim can act as an antenna picking up the radiated signal from the source, so be careful when designing circuit boards not to have large loops. Handheld radios, as often used in railway depots by staff on the ground, are a frequent source of problems. For example, when the marker light on the front of the 96 tube stock would switch on and off when a portable radio was used nearby. Eventually it was found that the victim was the 24 volt power supply for the lamp. In a similar vein, use of a radio next to speed transducer cables would cause one particular brake control unit to detect train movement. That's a great problem, except on one fleet where the toilet flushing mechanism was interlocked with a speed relay to prevent flushing onto the track when the train was stationary. And I'll leave you to imagine the effect of releasing the system in the depot. Some sources of electromagnetic interference. Intentional transmitters, i.e. broadcast radio and TV, mobile phones and radar, are a common source of interference. There's numerous stories of cars being, the locking system being disabled when close to a radio transmitter. High voltage power lines, both induced and radiated if you have corona discharge around the insulators. Domestic electric motors can be a source of conducted interference, for example, washing machine, fridge, electric drills. And of course lightning, which covers all coupling mechanisms, capacitive, conductive and radiated and induced. On the railway, the main sources are from the traction converters, both conducted and induced, arcing from the pantograph of the pickup shoe, which is radiated coupling, and track circuits. Note the track circuits are listed as a source. We're used to thinking of them as victims, but audio frequency track circuits can cause interference in nearby non-railway equipment.
Some examples of victims of electromagnetic interference. Radio and TV reception are susceptible to nearby radiating sources. Scientific and medical equipment is sensitive to mobile phones being used nearby. The picture shows the effect of an external magnetic field on a cathode ray tube oscilloscope. Some types of medical equipment are also sensitive to DC magnetic fields, for example MRI scanners, so a nearby DC railway can be a problem. On the railway, track circuits also appear as victims. Now, the main source of interference with railway equipment is generally other parts of the railway. However, nearby powerful intentional transmitters, such as broadcast TV or airport radio, have been known to cause problems. This slide looks at other electromagnetic issues which are often classed as EMC. Electrical systems compatibility, ESC, concerns line resonance on AC railways. It is an electromagnetic compatibility issue only in the sense that all electrical phenomena are electromagnetic. It's a system compatibility problem, but you cannot identify a source and a victim, so I don't regard it as electromagnetic interference. However, others may disagree with me. The effects of magnetic fields on the human body can be bad or even fatal in the extreme case. However, this area is covered by its own regulations and is not in the EMC regulations. It's an important topic, but I don't regard it as EMC.
The first case study concerns the Class 390 versus solid-state interlocking. Class 390 Pendolino started test running on the West Coast Main Line about 20 years ago. Solid-state interlocking was introduced in the UK in the 1980s. It comprises a central computer that uses trackside functional modules to interface with the railway hardware, i.e. signals, points, track circuits, etc.
This slide shows the SSI architecture. The SSI processor, in some central location, uses a dual redundant data bus called the trackside data link to communicate with the trackside equipment. The interface between the TDL and the TFMs is called the data link module, DLM. The TDL runs alongside the railway for many kilometres, so is subject to inductive interference. This slide contains some data that we need to try and understand what's going on here. 1. The maximum uninterrupted length of the trackside data link is 4 kilometres. This is so as to limit the maximum induced voltage for human safety. The worst case coupling factor, that's the induced voltage in the TDL conductors per amp in the overhead wires, is 25 volts per amp per kilometre at 11 kHz, which is in the TDL transmission band. The Class 390 spectrum has a peak in the line current spectrum of about 700 milliamps at 11 kHz. The TDL cable is assumed to have a common mode rejection ratio of minus 60 dB. What does this mean? It means that the ratio between transverse and longitudinal voltages is 1/1000. From this data, we can calculate that longitudinal induced voltage in the TDL is 70 volts, and then the transverse voltage is 1/1000th of that, which is 700 millivolts.
So what's the effect of this induced voltage on the trackside data link? Now, for most communications systems, a transverse voltage of 700 millivolts would swamp the signal. The Network Rail Guidelines for Demonstration of Compatibility with Telecom Systems gives a limit for sophomorically weighted transverse voltage of 1 millivolt. However, the SSI trackside data link was designed to work in a noisy environment. It uses a 4.5 volt output from the transmitter. The messages also use a safety protocol, so it's not credible that noise could cause a wrong action. However, if valid signals are not received, the receiver will go into safe state, which leads to disruption on the railway. And this is what was happening when the Class 390 came along. So why was the system being affected by noise at a level to which it should be immune? A simple circulation will explain why. This is a simple circuit model I built to illustrate what was happening on the SSI. It's not the real circuit, I don't have that information. It's just an example of how the induced interference might have been having the effect on the received messages. On the left-hand side, we have the transmitter at 11 kHz, floating with respect to ground, but anchored so each core is equal voltage to ground. Then we have the representation of the cable with the induced voltage in the middle. The data link module has assumed to have an isolation transformer, which links into a differential amplifier, followed by a Schmitt trigger, leading in as the signals go off to the trackside functional module. Around in the isolation transformer, there's assumed to be some stray capacitance between primary and secondary. This slide shows the output from the model for different degrees of interference. In each case, the blue signal is the input to the isolation transformer, and the green signal is the output from the Schmitt trigger. The red signal in the two centre slides shows the longitudinal voltage induced in the cable. On the left-hand side, we have no interference at all. We have a nice smooth input signal and output signal. In the second case, we have introduced 70 volts longitudinal voltage, but it's balanced. It's the same in each core. So again, there's no effect on the output. In the third case, we introduced an imbalance in the longitudinal voltage, 60 dB common mode rejection ratio. However, this is not enough to affect the output, as the Schmidt trigger rejects the slight perturbation. In the fourth case, we introduce a difference in the stray capacitance across the transformer, and here you can see there is now an effect on the output signal. So for the same what looks like the same input signal, we're now getting missing pulses and extra pulses.
Some observations on this case study. Firstly, a balanced cable is not sufficient. The input to the unit must also have balanced impedance to earth. In fact, the whole signal path from start to finish must have a balanced impedance to earth. This case had three coupling mechanisms in series. Firstly, conducted interference from the train onto the contact wire, and induced from the contact wire to the induced voltage in the line side cable, followed by capacitive coupling from the cable into the unit. Network Rail has recently updated its guidelines for compatibility with SSI to include a limit for train harmonic current in the frequency range used by the SSI TDL. NRGN SIG 50013 version 2 methodology for the demonstration of compatibility with interlockings specifies that frequencies greater than 10 kHz at 20 volts peak to peak should not be induced onto the trackside data link cable. Now 20 volts peak to peak is about 7 volts RMS, which is 10% of the estimated longitudinal voltage that we got for 700 milliamps on slide 19. The maximum current limit above 10 kilohertz would therefore be about 70 milliamps, which is about 10% of what the class 390 produces.
The second case study was my first experience with a real interference problem. The Dublin Area Rapid Transit started operation in 1984. It was a 1500 volt DC electrification around Dublin Bay. It was 42 car EMUs equipped with DC motors and a 3 thyristor chopper traction drive. Train testing and driver training started during the spring of 1984 prior to the start of service. Shortly after testing started, the Irish state broadcasters received complaints from people living near the track that their radio reception was being interfered with, both on local medium wave stations and also BBC Radio 4 on long wave. The interference took the form of a single frequency tone that was annoying on the medium wave stations and completely drowned out the long wave program content.
When the train commissioning team heard of the complaints, we decided to investigate. We took our precision scanner out to the depot test track in mobile form and drove a train up and down for a bit. The effect on reception was immediately apparent, and the single tone was at 327 Hz, the chopper frequency, so we could not deny that the train was the source. The overhead wires were acting as a long antenna, but what was the coupling mechanism between the chopper and the overhead wires? This diagram shows a simplified version of the chopper circuit in its motoring configuration, with the chopper and the motor over here, line filter capacitor and inductor up to the pantograph and onto the overhead line. These, however, are the intentional components. There is also some stray inductance in the cabling between the chopper and the filter capacitor. When the chopper switches off, there is a short oscillation between the stray inductance and the filter capacitance. This appears in the filter voltage, but also on the pantograph voltage. The oscillation took the form of short bursts at 2 MHz, with a repetition rate of 327 Hz, the chopper switching frequency. Hence the hum picked up by the radios. But the inductor is there to stop harmonic frequencies getting onto the line, isn't it? Now remember that wound components can have significant stray capacitance between windings. So at 2 MHz, the inductance looks more like a capacitor with low impedance. Conclusion: don't forget stray capacitance and inductance, especially when dealing with high frequencies. This case actually had two coupling mechanisms, capacitive from the train to the overhead line, and radiated from the overhead line to the radio receivers. And what was the solution? Well, we added a 2 microfarad capacitor between the pantograph and the ground of the car body. Thank you.